So what we have proved in the second theorem, the second choice theorem, is that if you have a completely positive map omega, the only condition we have is omega is a completely positive map, then we can find at least one set of operators kn such that the map, the action of the map omega on operator rho can be written as sum over n kn rho kn dagger. And this we achieved by assuming or by finding a very special operator E such that the ijth block in that E is the ijth matrix. So because ij matrix is the basis for an arbitrary operator, if we can find the action of the map omega on ij, we can find the action of omega on any arbitrary operator rho. This is what we did, and we found the operator sum representation or cross operator representation of the omega. So what the first theorem of Choi says that operator sum representation implies completely positive map. And second one says that completely positive map implies operator sum representation. Okay, so it means all the positive map can be written in the operator sum representation, and operator sum representation can be written in terms of the positive map. Is a completely positive map. So with this, we are done with the proof of the choice theorem. Just to connect it with what we have already done, for positive maps also, we found that H can be written as sum over n lambda n kn out of product kn. Okay, or the action of omega on a matrix A could be written as sum over n lambda n kn A kn dagger, but lambda n need not be all positive. Need not be all positive semi-definite. Okay, but for completely positive map, omega of A can be written as sum over n lambda n kn A kn dagger, where lambda n are all positive. This is the difference between positive map and completely positive map, but this condition is not enough for positivity of the map, because this condition only assumes this condition can be only derived from the hermiticity condition, not the positivity condition of the map. But all the positive maps are Hermitians also, so this condition is valid for, this condition is necessary but not sufficient for all the positive maps. But this is a necessary and sufficient condition for the completely positive map. So in that way, there is a relation between positive maps and completely positive maps. If we want to see, then there is a set of all the maps. It's a graphical representation. So all the maps we have. Then there is a subset of these maps which are Hermitian maps. Then there is a smaller subset of it which are positive maps. And there is a smaller subset, further smaller subset inside it. Which are CP maps. So all the maps, then Hermitian map, then positive map, and all the CP maps. This small subset of maps is what represents the physical states on a quantum system. Only these maps, not all the other maps. So far, we have been only saying that completely positive maps represent physical processes, and all the physical processes can be represented by completely positive maps. But in this lecture, we will establish that connection and give a formal proof of this statement. But before that, we need to understand what we call a physical process. In quantum mechanics, only unitary transformations are valid transformations. It means only unitary transformations can transform one state to another state. So as far as quantum mechanics of a isolated quantum system is concerned, only unitary processes are physical processes. If we assume that there is nothing beyond our existing universe, the universe we see, if there is nothing outside that universe, then that universe, entire universe, forms an isolated quantum system. It means the dynamics of the whole universe will be a unitary transformation. So if we are interested in a dynamics of a system S, then we can think of it as S plus the entire universe, or we call it ancilla, some assisting universe or assisting quantum system. So the total Hilbert space is HA, tensor HS. So any process which can be defined, any process on Hilbert space HS, if we can define it as a unitary process on HA tensor HS and the reduced dynamics of that only on the system, then we will call it a physical process. What I mean is, if we have a dynamics or a process which takes rho to rho prime, where rho belongs to the set of operators acting on HS, then rho is a state of system S. The process takes rho to rho prime. If we can write it as a unitary process on state rho A of ancilla, tensor rho S or rho of the system, U dagger, and then traced over ancilla. If the dynamics or the process we are interested in, the physical process, if that can be represented by the unitary action of on the system and ancilla and tracing out the ancilla, then we will call it a physical process. So in other words, if the desired process can be achieved by a unitary transformation on an enlarged system, then this process must be physical. So whenever we say physical process now onward, this is what we will mean. Now the point is, from the Choi theorem, we know if omega is a completely positive map, then action of omega on rho can always be written as sum over I, ki rho, ki dagger. So this is the crux of the two Choi's theorems. And if we want the trace of the achieved state to be preserved, so rho of omega of the trace of omega of rho to be 1 for all the rows, then it means sum over I trace of ki rho ki dagger must be equal to 1. One equality I would like you to verify, that if we have trace of product of three matrices A, B and C, then it is same as trace of C, A, B. This is the cyclic property of the trace. We can use this property, then we get trace of ki rho ki dagger to be equal to trace of ki dagger ki rho. Hence trace of omega rho becomes sum over I trace of ki dagger ki rho to be equal to 1 for all the states rho such that trace of rho is 1. This is true for all the states rho. It means that sum over I ki dagger ki must be identity. So this condition over the operators ki is the condition for trace preserving nature. So omega of rho for a completely positive and trace preserving map can be written as sum over I ki rho ki dagger, and ki dagger ki sum over I is identity. Now we have to find a unitary process. We have to, in order to show that this completely positive map can be achieved, it represents a physical process, then we need to find an ancilla HA, the Hilbert space of the ancilla, and the initial state rho A of the ancilla, a unitary operator U, such that the action of U on rho A tensor rho and then tracing out the ancilla gives us completely positive map. So the initial state, let us say rho AS is rho A tensor rho, where rho is the state we are interested in. After that, we do the unitary transformation. Then we get rho tilde AS to be U rho A tensor rho U dagger. And then we trace over ancilla. We get rho tilde, which is trace over ancilla U rho A tensor rho U dagger. Let's let us assume that rho A is a pure state, and let us remember that trace over operators Z is sum over n z n, where n is the orthonormal basis. So we use these two and we get trace over, or we get rho tilde to be sum over n. We are taking trace over only over one subsystem, so n tensor identity on the other. U rho A is psi tensor rho U dagger n tensor identity. So this is our rho tilde. Now let us define Kn, which is n tensor identity U psi tensor identity. So we are projecting the ancillary space on the state n on the left side and psi on the right side. So U is an operator acting on ancilla and system, and we are projecting it in the n psi space, so that the leftover operator is the operator acting on only the system. So Kn are the operators acting on the system. So with this definition, we can see that rho tilde is sum over n Kn rho Kn dagger. So in that way, every physical process is represented by the unitary operator U and the ancilla state psi. We can always get operator sum representation. Hence, it's a completely positive map. But next question we want to answer is, given a completely positive map omega, whose action is represented by sum over I, Ki rho Ki dagger, can we find a unitary operator U and the state psi corresponding to this set of operators Ki's? Okay. Now you see Ki is, or Kn is n, which let us take to be the computational basis, U tensor identity, U and psi tensor identity. For simplicity, let us say psi is the zeroth computational state. So it means it is 1 0 0 0 0 and so on. And n is also a computational basis, so it will be 0 0 0 1 0 0 0, where this is the nth position. And U can be written as sum over ij, I out of product j tensor small uij. Okay, so it means we can write it as U11, U12, U13, U21, U22, and so on, where U, Ij are the operators acting on the Hilbert space of the system. So it means n tensor identity U 0 tensor identity is U and 0, and which is Kn. So it means U11, sorry, it's 0. This is 1. The counting is from 0, not from 1. So U10, U20, U30, and so on are K1, K2, K3, and so on. So it means the unitary, if we choose unitary to be of the form K0, K1, counting is from 0. So let me make this also 0. That's K2 and Kn, and there were n projectors or n k operators. From here, we can see that the first column of operators is occupied by the cross operators ki's, which represent the completely positive map omega, and and U must be a unity operator. So the rest of the matrix R is chosen in such a way that the U is unitary and a square matrix. Okay, and this R is completely arbitrary. We can choose anything as long as U is unitary. This with the initial state of the ancilla to be computational state 0, we have found a physical process corresponding to the completely positive map omega given by the cross operators, represented by the cross operators kx. So in that way, we have shown that physical process given by unitary operator u and initial state of the ancilla psi. This corresponds to a set of cross operators kn, and a set of cross operators kn. We can always find a unitary u or acting on ancilla and system together jointly, and the state of the ancilla to be psi. Let me repeat. What we have shown is for a given unitary acting on ancilla and system and the initial state of ancilla, this corresponds to a completely positive map CP given by the cross operators Kn. Reverse in alternatively, if we are given a set of cross operator, we can always find a unitary U acting on system and ancilla and a initial state of the system. So in that way, completely positive maps represent physical processes and physical processes represent completely positive maps, and hence we have established the relation between the completely positive maps and physical processes. There are some properties of cross operators and completely positive maps which we need to keep in mind. First of all, for a map omega, sum over n, kn, rho, kn, dagger, the choice of kn is not unique. So there exist Rm such that Rm, rho, Rm, dagger, sum over m is also omega of rho. To prove this thing, let us say Rm is chosen in such a way, it's a W, Nm, Kn. Okay, so and sum over n. Then Rm, rho, Rm, dagger, sum over m can be written as sum over n, n prime, and m, W, Nm, Kn, rho, W star, n prime m, Kn prime, dagger. We can write it as sum over n, n prime, W, Nm, sum over m, W, Nm, W star, n prime m, Kn, rho, Kn prime, dagger. Sum over n or m, W, Nm, W star, n prime m is sum over m, W, Nm, W dagger matrix, and m, n prime element. Now you can see this is the product of W and W dagger. So this is the product of W and W dagger, and they're jointly n prime element. Now, if we choose, it means W is isometric. Then W dagger n prime is delta n prime. It means sum over m rm rho rm dagger becomes sum over n prime delta n prime kn rho kn prime dagger, which is same as sum over n kn rho kn dagger. So in that way, if the two set of cross operators are related by an isometric matrix, then they will represent the same completely positive map. Hence, the choice of the cross operator is not unique. To find the set of cross operator for a given completely positive map omega, what we need to do is we apply omega and find the KL element sum over ij mij KL rho of KL. So from here we can find the matrix representation of omega, that is M. From M we can find the H representation, and these two are related as follows: Mij KL equals H Ik JL. We have done it earlier when we were talking about the positive maps. And for since H is positive, we can show that for completely positive map H is positive and H is Hermitian, of course. Then H can be written as sum over n lambda n kn kn, where lambda n are the eigenvalues and kn are the orthonormal eigenvectors of H. And from here, let us put tilde here for normalized, and sum over n kn kn, where these are unnormalized. Kn is defined as sum over square root of lambda n kn tilde. Kns are the unnormalized vectors. From here, H sum over n kn lambda n, we can show that omega of rho is sum over n kn rho kn dagger, where kn are the folded version of the kns. It means we convert a vector into a matrix, and then that's how we get the cross operator kn. This is one choice of cross operator, and this is in some sense it's a canonical choice of cross operator because they are achieved from the spectral decomposition of the H matrix. Now we can use the isometric transformation on kns, and we can generate large number of set of operators which represent the same CP map, and we can choose the most convenient cross operators for us. In that way, we can find the set of cross operator for any given completely positive map.